At 9:23 in the morning on June 12, 1944, British engineers at the Fighting Vehicles Proving Establishment in Chertsey, Surrey, prepared to evaluate a German Panther tank that German propaganda claimed was invincible. The tank was a Panther Ausführung D, serial number 213101, built by Maschinenfabrik Niedersachsen Hannover in June 1943. The Soviets had captured it on the Eastern Front and shipped it to Britain for evaluation. British engineers had been testing armoured vehicles at this facility since 1942. They understood tanks, their engineering, their strengths, their weaknesses. But the Panther was different. This was the tank that German newsreels showed crushing Soviet opposition, the tank that Wehrmacht training films portrayed as technologically superior to anything the Allies possessed, the tank that British tank crews would face in Normandy within weeks. The Panther had specifications that looked impressive on paper. 45 tons of combat weight, a 690 horsepower Maybach HL230 engine, governed to 2,500 revolutions per minute, limiting output to approximately 600 horsepower under operational conditions. Maximum road speed of 46 kilometers per hour. Frontal armor 80 millimeters thick at 55 degrees. A 7.5 centimeter KWK-42 gun, with a muzzle velocity of 935 meters per second, using standard armor-piercing ammunition. On paper, it was a formidable weapon system. In reality, British test teams at the Fighting Vehicles Proving Establishment were about to discover something that German High Command already knew but refused to acknowledge. The Panther was a mechanical disaster. The British testing program was straightforward. They would put the Panther through the same trials they used for British tanks: cross-country mobility tests, road speed trials, suspension, evaluation, hill climbing, brake tests, endurance runs, the same procedures they used for the Churchill, the Cromwell, the Sherman. Standard evaluations that every British tank passed routinely. What the evaluation team did not know was that they would never complete the full testing program. The Panther would not survive long enough. The first problem appeared during the initial trials. Test drivers reported that third gear had failed completely. The transmission would shift into second gear, shift into fourth gear. But third gear produced nothing but grinding noise and continual jumping out. The test crew included experienced tank drivers with years in the Royal Tank Regiment. They had driven every British tank in service and several captured German vehicles. They knew the difference between operator error and mechanical failure. They knew when a gearbox was being stubborn and when it was actually broken. This was mechanical failure. Complete failure. The Panther's transmission was a 7-speed gearbox, 7 forward gears and 1 reverse, designed to provide precise control over the tank's speed. But the complexity of the transmission made it fragile. Each gear shift required precise synchronization. Each component had to function perfectly. When drivers tried to engage third gear, something inside the gearbox had already failed. A synchromesh ring, perhaps, or a sliding collar. The gear teeth were not meshing. The transmission was eating itself from the inside. The evaluation team noted the gear problem in official logs. Third gear inoperative, cause unknown. The team continued testing without third gear. The evaluation protocols did not require a working third gear for most tests. They could work around it. British tanks with failed gears had completed trials before. So a single failed gear was not enough to stop the evaluation. What they could not work around was what happened next. During the suspension tests on rough terrain, the Panther exhibited a behavior that confused the evaluation team. The double torsion bar suspension system, supposedly one of the Panther's advanced features, felt harsh and uncomfortable. The nose dipped violently when hitting bumps, bottoming out the front suspension completely. The crew inside reported being thrown around with enough force to cause bruising. This made no sense to the engineers. The Panther's suspension looked sophisticated, dual torsion bars for each of the 8 interleaved road wheels on each side, 18 road wheels per side, 36 wheels total, all overlapping in an intricate pattern. German engineering had focused on creating a smooth ride with excellent weight distribution. Yet the reality was a suspension system that performed worse than the relatively simple suspension on British tanks like the Churchill. The evaluation team set up instrumentation to measure suspension performance objectively. Accelerometers mounted inside the crew compartment, cameras to record, suspension travel. The data confirmed what the crew felt. The Panther's suspension had a very short travel distance before bottoming out. When the front road wheels hit an obstacle, the suspension compressed quickly and then hit the stops with jarring force. The theoretical advantage of the dual torsion bar system, that it could handle higher loads with better damping, was not translating into better crew comfort or better cross-country performance. By comparison, when they ran the same tests with a Churchill 7, the Churchill's suspension absorbed the same obstacles with much less violence. The Churchill used a coil spring suspension system with 11 road wheels per side on each track, simpler, heavier, but more forgiving. The Churchill crew reported a comfortable ride even over rough terrain. The Panther crew reported feeling every bump. Members of the evaluation team who rode in both tanks during the cross-country trials noted that crew fatigue would matter significantly in the combat. A crew that was being beaten up by their own tank's suspension would be slower to react, less accurate in gunnery, more exhausted after a day of operations. The Panther's harsh ride was a tactical disadvantage, not just a comfort issue. The road speed trials produced more disappointment. German specifications claimed the Panther could reach 46 km per hour on roads. The British team verified this specification on good road surfaces. Cross-country speed was worse. The Panther averaged slower speeds than the Churchill 7 across rough terrain, despite the Churchill being a heavy infantry tank not designed for speed. The Panther was supposed to be a medium tank, emphasizing mobility, yet it moved like a heavy tank without the heavy tank's armor protection on its sides and rear. The first fire happened on June 14th during hill climbing tests. The testing protocol required climbing steep slopes at Farnham Park. British tanks climbed these slopes routinely. The Cromwell could sprint up them in second gear. The Churchill crawled up in first but made it reliably every time. The Sherman handled the grades without issue. The Panther climbed to the top of a 40-degree slope successfully. Then the test protocol required driving back down. The test driver positioned the tank for descent and engaged reverse gear. The Panther started rolling backward down the slope under controlled descent, standard operation for this type of test. Then, partway down the slope, everything went wrong. The engine backfired. Not a small backfire, a pop or a cough. A massive explosion inside the engine compartment. The sound was like a bomb detonating. The force was strong enough to blow the engine access hatches partially open, the latches unable to hold against the pressure wave. Fire erupted immediately around the fuel pumps on the front near-side corner of the engine bay. Orange flames shot out, not the red flames of burning wood or paper, the distinctive orange of burning gasoline. Black smoke poured from the engine compartment, thick and toxic, the acrid smell of burning fuel and hot metal. The test driver brought the tank to an emergency stop, killed the engine, opened his hatch. Crew training took over. The four-man crew, driver, radio operator, gunner, commander, evacuated immediately through their respective hatches. They were on the ground and away from the tank within 10 seconds. The fire suppression team rushed forward with Perini fire extinguishers, the standard fire suppression equipment for vehicle fires. 2 men on each side of the engine compartment, spraying the chemical extinguishing agent into the flames. The fire fought back for a moment, flaring up where air reached it, then died under the chemical assault. 30 seconds from ignition to suppression. Quick response, good training, prevented a total loss. When engineers examined the engine, they found no serious damage from the explosion itself. The backfire had not destroyed any major components. The fuel system was intact. The engine would still run. But the fact that it happened at all was concerning. Backfires powerful enough to blow open access hatches and start fires were not normal. Engineers noted in their report that the high compression ratio of the Maybach engine made it susceptible to unusual combustion events. The design created conditions for catastrophic backfires. The problem was fundamental to the engine architecture. They repaired the fire damage and continued testing. The Panther needed to be evaluated fully. British tank crews would be facing these machines in combat within weeks. The Normandy landings were scheduled for early June. The War Office needed comprehensive data on the Panther's capabilities and vulnerabilities, so the trials continued despite the fire incident. The evaluation team conducted pitch and roll tests on June 14th. They drove each test vehicle, including the Panther, over a course with ramps and obstacles at various speeds: 10 miles per hour, 15 miles per hour, 20 miles per hour. A camera mounted on the turret recorded the pitch and roll oscillations. This test evaluated suspension performance and crew comfort during tactical movement. The Panther's results were contradictory. The camera data showed the suspension damped out oscillations quickly, faster than British tanks. But every member of the evaluation team who rode in the Panther during cross-country movement reported that the ride was uncomfortably harsh. The suspension felt stiff, unyielding. The contradiction suggested the Panther's suspension was optimized for measurements that looked good on paper, but failed to translate into actual crew comfort or operational effectiveness. The second fire happened on July 28 during endurance trials at Long Valley. The protocol required running the tank around a test course repeatedly to evaluate mechanical reliability under sustained operation. The Panther had completed one full circuit of the course. On the second lap, the steering needed adjustment, standard procedure when steering response degraded. The test driver brought the tank to a halt and switched off the engine. Immediately, thick smoke began filling the turret. The smoke was coming from the engine compartment. Within seconds, an explosion ripped through the engine bay. The floor of the engine compartment ignited. Flames spread rapidly. This fire was more severe than the first one. The entire engine compartment was engulfed before the crew could react. They evacuated immediately. The fire suppression team rushed in, but the fire had already spread too extensively. The Maybach engine burned intensely. Fuel lines melted. Hydraulic fluid ignited. The heat was strong enough to warp metal components. By the time they extinguished the flames, the Panther's engine compartment was destroyed beyond economical repair. Engineers examined the wreckage carefully. The official report documented their findings in detail. The fire had started with another backfire, this one occurring after the engine had been switched off. Some incandescent substance, probably carbon buildup on the spark plugs or a piece of glowing carbon in the combustion chamber, had ignited fuel vapors in the engine. The backfire blew fuel and oil vapor through the air cleaners, which were oil bath-type filters mounted centrally on the engine. The inlets to the air cleaners were positioned underneath the units. When the backfire occurred, it sprayed oil and fuel vapor directly onto the hot valve covers and exhaust manifolds. With the engine hot from operation, the vapor ignited immediately. The explosion that followed was violent enough to rupture the flexible fuel lines, and burning fuel poured into the engine compartment. The Panther had burned itself out from the inside. The trials on this machine were abandoned. The Fighting Vehicles Proving Establishment issued their report in May 1944, though testing had only been completed in late July. The conclusions were damning. The Panther compared very unfavourably with any British tank in service. The amount of mechanical trouble experienced during the limited trials was unacceptable. Third gear failed immediately and remained inoperative throughout testing. The suspension performed poorly despite impressive technical specifications. The engine was prone to catastrophic fires. The report noted that many of the test results were inconclusive because the tank had failed mechanically before the team could complete the full evaluation program. The official report document number FT1391 became a key intelligence document, circulated to British tank units preparing for Normandy operations. The report included specific comparisons with British tanks. Across country, the average speed was rather less than that of the Churchill 7, despite the Panther being classified as a medium tank versus the Churchill's heavy tank designation. On roads, the maximum speed had been verified at approximately 30 miles per hour, matching German claims. But the critical finding was reliability. The report stated plainly that the amount of mechanical trouble experienced on this trial suggested the Panther compared very unfavourably with any British tank now in service. Regarding the suspension, while camera pitch records showed a marked ability to damp out oscillations, the opinion of all members of the evaluation staff who had ridden across country in the tank was that the suspension was not good. The ride was harsh, uncomfortable, and would contribute to crew fatigue in extended operations. But the story of British evaluation of German Panthers was not finished. In fact, the experience with that first Soviet-captured Panther in summer 1944 would be repeated on a much larger scale 3 years later, with consequences that would finally demonstrate beyond any doubt the myth of German technical superiority in tank design. The war ended in May 1945. As British forces advanced into Germany, they captured vast amounts of German equipment. In the city of Hannover, which fell to British Ninth Army in April 1945, the British discovered one of the 3 major Panther assembly plants. The Maschinenfabrik Niedersachsen-Hannover facility, known as MNH, had been building Panthers since early 1943. When British forces arrived, they found the assembly lines partially destroyed by Allied bombing raids in mid-March 1945, but significant numbers of Panther components remained. Engines, transmissions, hull sections, turrets, gun systems, all waiting to be assembled. The British occupation forces included the 823 Armoured Troops Workshop of the Royal Electrical and Mechanical Engineers, known as REME. This unit specialised in repairing and maintaining armoured vehicles. They arrived in Hannover on June 8, 1945, and initially set up operations at the Hanomag factory. Their commanding officer, Captain William J. Hadlow, received orders from British Army of the Rhine headquarters to complete as many Panther tanks as possible from the remaining components at the MNH facility. The purpose was straightforward. The British needed Panthers for comparative testing against British tank designs. They needed to understand exactly how the Panther compared to British tanks like the upcoming Centurion and the experimental Black Prince heavy tank. The 823 workshop relocated to a factory in Laatzen, south of Hanover, on June 29, 1945. The main MNH assembly line at Linden was too heavily damaged to use, but the Laatzen facility was largely intact. Laatzen had been a sub-assembly plant during the war, producing track links, gun tubes, and various smaller components for Panthers. The building had good overhead lighting, functioning roof structure, and adequate workspace for the assembly project. Captain Hadlow organised the efforts systematically. He was a trained Royal Electrical and Mechanical Engineers officer with expertise in vehicle recovery and repair. German workers who had been building Panthers during the war were retained to assist. These men knew the Panthers' systems intimately. They had built hundreds of them during the war years. Many were ambivalent about helping the British. Germany had lost the war, but national pride remained. However, they needed jobs, they needed money, their families needed food. The British paid them in occupation marks and provided rations. Practical considerations overcame political ones. British REME mechanics supervised the assembly process, learning as they worked. The process revealed how different German engineering philosophy was from British practice. British tanks were designed to be maintained in field conditions with basic tools. Components were accessible, replaceable, often interchangeable between models. German tanks, especially the Panther, were engineered like precision machines. Tight tolerances, complex interactions between systems, components that required specialized tools to access or adjust. Maintaining a Panther properly required resources and expertise that would not be available in combat conditions. The Panther was an assembly plant tank, not a field maintenance tank. The assembly team used original German quality control procedures. Each chassis had to be test-driven for 15 kilometers without the turret mounted to verify proper functioning of the automotive components. Engine operation, transmission performance, steering response, track tension, suspension function, everything checked systematically. After mounting the turret, which weighed several tons and required an overhead crane to position correctly, the complete tank had to be driven for another 50 to 60 kilometers. These were standard German acceptance protocols, the same procedures MNH had used during wartime production. The finished Panthers were tested on the nearby heathland around Lützen, driven by REME drivers with German mechanics riding along to provide guidance. Mechanics noted that even these brand-new Panthers, assembled carefully with quality components in good conditions, developed problems quickly. Oil leaks appeared around valve covers. Coolant leaks emerged from engine seals. Steering became progressively stiffer as the clutches wore in. These were new tanks, assembled from new parts, and they were already showing maintenance issues during initial break-in periods. The work took 9 months. From August 1945 through spring 1946, the 823 workshop completed 9 Panther tanks and 12 Jagd Panthers, the tank destroyer variant built on the Panther chassis. Each completed vehicle received a small brass plaque welded to the front glacis plate. The Setches Reforme 2 Main A Fizz. Plaques identified the tanks as assembled by 823 Armoured Workshop REME, British Army of the Rhine, at MNH Hannover. These were brand new Panthers, built to the same specifications as wartime production, but assembled under British supervision after Germany's surrender. The plaques served as permanent documentation of this unique assembly operation. In late 1947, the Fighting Vehicles Proving Establishment at Chertsey received 5 of these vehicles for comprehensive testing: 2 Panther tanks, 2 Jagd Panthers, and 1 Berg Panther armoured recovery vehicle. The plan was ambitious. They would subject all 3 Panther variants to the complete British acceptance trial programme. Every test that a new British tank had to pass, these Panthers would face. The trials would provide definitive data on how the Panther compared to British armour: cross-country mobility, road performance, hill climbing, endurance, reliability, everything. Finally, the British would have comprehensive, scientific data on the tank that German propaganda had portrayed as invincible. Testing began in February 1948. The vehicles were loaded to full combat weight with ballast plates to simulate ammunition, fuel, and crew equipment. The Panther tanks weighed 44.5 tons. The Jagd Panthers weighed 46 tons. The Berger Panther weighed 42.5 tons. All 5 vehicles were essentially new. The Panthers and Jagd Panthers had been assembled in 1945 and had minimal running time since assembly. The Berger Panther had run 632 kilometers before arriving at the establishment and needed a new engine installed before trials could begin. With the exception of spare engines, no spare parts were available. The vehicles would have to complete the trials using only the components they had been assembled with. Within days of starting the trials, it became apparent that completing the full test program would be impossible. The Panthers were failing mechanically at an alarming rate. Steering mechanisms malfunctioned. Engines caught fire. Transmissions broke down. The test team, led by engineers from the Fighting Vehicle Design Department, quickly realized they would have to modify their approach. The original plan to test all 3 Panther variants separately was abandoned. Instead, they would focus on getting whatever data they could from whichever vehicles remained operational, cannibalizing the broken ones for spare parts to keep others running. The first major failure occurred during initial cross-country trials. One Panther tank suffered complete failure of its steering mechanism. The exact failure mode was instructive. The Panther's steering system used clutch and brake steering. To turn left, the driver engaged a clutch that disengaged power to the left track and applied a brake to slow that track. The tank would pivot toward the slowed track. To turn right, the same process, on the right side. This system worked acceptably on flat ground at moderate speeds. Under stress, in rough terrain, making sharp turns, the system failed catastrophically. During the cross-country trial, the test driver attempted a sharp left turn while traversing a rutted section of the course. He engaged the left steering clutch and applied the left brake. The clutch slipped. Instead of disengaging smoothly, the clutch burned. The friction material overheated. Smoke began coming from the clutch housing. The steering became erratic. The driver tried to compensate, but the clutch was destroyed. The left side steering mechanism was completely inoperative. The tank could only turn right. It was impossible to control properly. The driver brought the Panther to a halt and reported the failure. The tank was withdrawn from testing immediately and stripped for parts. The destroyed clutch assembly was removed and examined. The friction surfaces were burned black. The clutch had overheated from excessive load and failed completely. This was a design inadequacy, not a manufacturing defect. The clutch was not sized appropriately for the loads the Panther's weight created during hard steering maneuvers. The second Panther tank developed engine problems almost immediately. During cross-country running, the Maybach engine began overheating. Temperature gauges climbed into the red zone. Coolant temperature exceeded 100 degrees Celsius. The test driver reported warning indicators on the instrument panel. He reduced speed, but the temperature continued climbing. Something in the cooling system was not functioning properly. The Panther's cooling system was complex. The engine compartment was sealed, designed originally for the Panther to be amphibious, though that capability was never actually implemented in production. The sealed engine compartment created cooling challenges. Air intake and exhaust required ducting. Coolant had to circulate through radiators mounted in specific positions. Any restriction in the cooling airflow, any blockage in the coolant passages, and the engine would overheat rapidly. The test driver continued the test run according to protocol. The temperature was high, but not yet at critical failure levels. Then came the familiar pattern that British engineers had seen 3 years earlier. The engine backfired. A sharp bang, like a shotgun blast inside the engine compartment. Explosion in the engine bay. Fire erupted immediately. Orange flames visible through the engine deck grills. Black smoke poured out in thick clouds. The driver shut down the engine immediately and evacuated. The fire suppression team rushed in, but this fire was more severe than they had dealt with during the 1944 testing. The flames had spread to multiple fuel lines. The heat was intense. Fire extinguishers could not suppress it completely. By the time they got the fire under control, the engine was destroyed. Valve covers melted, fuel lines burned through, wiring harness incinerated. The carburetor was damaged beyond repair. The Maybach HL-230 engine, which had cost thousands of Reichsmarks to manufacture during the war, was now scrap metal. This Panther was also withdrawn and designated as a spare parts source. Its transmission, steering clutches, road wheels, anything salvageable, went into the spare parts inventory to keep other Panthers running. The first Jug Panther lasted longer, but not by much. It completed several test runs successfully. The team began to hope they might get useful data from at least one vehicle. Then, during an endurance run, the transmission failed catastrophically. Gears stripped inside the gearbox. The vehicle lost all forward drive capability. It was towed back to the maintenance area and cannibalized for parts. Internal examination showed that gear teeth had broken under load, a sign that the transmission components were not adequately robust for the vehicle's weight and the stress of sustained operations. The second Jagd Panther became the primary test vehicle by default. It was the last one still capable of movement. The team concentrated all their efforts on keeping this single vehicle operational. They completed some mobility tests, some road speed runs. But the Jagd Panther was deteriorating rapidly. The steering became increasingly difficult to operate. The transmission was making concerning noises, grinding sounds during gear shifts, metallic clanking during hard maneuvering. The engine was consuming oil at an alarming rate, requiring top-ups after every test run. During the hill-climbing trials, disaster struck. The test protocol included brake-holding tests on steep slopes. This was critical for evaluating whether a tank could hold position on slopes during combat, important for defensive operations where tanks needed to fight from hull-down positions on hillsides. The Jagd Panther was driven to the top of slope number 4, a 35% grade incline, steep enough that most wheeled vehicles could not climb it at all. The tracked Jagd Panther climbed it successfully, the Maybach engine pulling the 46-ton vehicle upward steadily. At the top, the test driver positioned the vehicle nose upward on the slope and applied the brakes. The protocol required holding the vehicle stationary on the slope for 30 seconds, then releasing brakes and driving forward over the crest. simple test, performed routinely on British tanks. The driver applied the brakes. The Jagd Panther held for perhaps 5 seconds. Then the brakes failed. The driver felt it through the brake pedal, a sudden loss of resistance. The pedal went to the floor. The Jagd Panther began rolling backward down the slope. 46 tons of steel and armor, accelerating in reverse down a 35% grade with no brakes. The driver tried to steer, tried to control the descent, but the vehicle was gathering speed. The steering responded sluggishly. At first, then not at all. The Jagd Panther was rolling faster, building momentum with each meter of descent. At the base of the slope was a tree stump, a large oak stump, perhaps half a meter high, left from land clearing years before. The Jagd Panther hit the stump at approximately 25 kilometers per hour. The collision was violent. The entire vehicle shook from the impact. The crew inside were thrown forward against their restraints. Metal screamed as the hull struck the immovable obstacle. The impact broke a torsion bar, one of the massive steel bars that supported the road wheels and provided suspension. The broken torsion bar, under tremendous spring tension, punched through the side wall of the gearbox like a spear penetrating armor. The transmission housing was breached. Transmission oil poured out onto the ground. Gears inside the gearbox were knocked out of alignment. The transmission was destroyed. The last functional vehicle was now disabled beyond repair with available resources. The crew evacuated, shaken but physically uninjured. The Jagd Panther sat at the base of the slope, immobile, leaking transmission oil onto the ground. Engineers examined the damage. The torsion bar had penetrated completely through the gearbox housing. There were no spare gearboxes available. The vehicle could not be repaired in the field or even in the workshop without factory-level resources. The Berger Panther, the armoured recovery vehicle, was pressed into service for testing despite not being a combat tank. The team attempted to complete the 25-mile cross-country endurance trial with it. The Berger Panther's gearbox failed partway through the test. With no spare parts available, no operational vehicles remaining, and all test vehicles either destroyed by fire or disabled by mechanical failure, the trials had to be suspended permanently. The Fighting Vehicle Design Department issued their final report in February 1948. The report was brief and blunt in its conclusions. Owing to the inherent unreliability of the steering mechanism and the proclivity of the engine to catch fire, it had been impractical to cover the full trials program. The original intention of testing all 3 Panther variants had been abandoned early in the test program. Results were incomplete because all available vehicles had been put out of action due to major mechanical failures before testing could be completed. Very little information of any value was obtained from the trials. The reason named for this failure was the general mechanical unreliability of the Panther and Jagd Panther tanks. The report concluded with a stark recommendation. Close this project. Further testing would serve no purpose. There were no more serviceable vehicles to test, no spare parts to repair damaged ones, and the vehicles that had been tested had demonstrated such poor reliability that additional data would not change the fundamental conclusion. The contrast between German propaganda and British testing reality was absolute. German newsreels had shown Panthers as invincible. German technical documentation portrayed the Panther as sophisticated and advanced. Wehrmacht training materials emphasized the Panther's superiority over Allied tanks. Yet when British engineers subjected these tanks to the same routine tests that British tanks passed regularly, every single Panther failed catastrophically. Not one completed the standard acceptance trials. Not one. 5 vehicles tested, 5 vehicles destroyed or disabled by mechanical failure. 0 successful completions of the test program. What British test teams had discovered through 2 separate evaluation programs, the 1944 testing of the Soviet-provided Panther and the 1947-48 testing of the REME-assembled Panthers, was that the Panther embodied a fundamental flaw in German tank design philosophy during the war. The Germans had prioritized specifications that looked impressive on paper: thick armor at extreme angles, high-velocity guns with excellent penetration, advanced suspension systems with sophisticated engineering, but they had failed to ensure these components could work together reliably in field conditions. They had failed to design for maintainability, for ease of repair, for operation by average crews under combat stress. The Panther had been rushed into production in 1943 to meet Adolf Hitler's deadline for the Kursk offensive. The deadline was absolute. Hitler had ordered Panthers ready by July 1943 for Operation Citadel, the massive German offensive intended to pinch off the Kursk salient. The design had been finalized in January 1942, but testing was cut short, problems were glossed over, production began before the design was mature. The result was catastrophic. The early production Panthers sent to Kursk in July 1943 had been mechanical disasters. German military records document the failure in painful detail. The 200 Panthers that deployed for Operation Citadel suffered catastrophic mechanical failure rates that exceeded combat losses. On July 5, 1943, the first day of the offensive, only 40 Panthers remained operational by evening. The rest had broken down. Transmissions failed. Final drives broke. Engines overheated and caught fire. Steering systems failed. Panthers were burning spontaneously without being hit by enemy fire. Internal fires were destroying tanks that had never been engaged by Soviet forces. German commanders at Kursk filed detailed reports about Panther failures. General Heinz Guderian, Inspector General of Armored Troops, visited the front during the battle. He observed Panthers firsthand in combat conditions. His reports noted that final drives were failing catastrophically, that transmissions were breaking after minimal use, that engines were catching fire infrequently. Guderian recommended halting Panther production until the fundamental problems could be resolved. His recommendation was ignored by higher command. Germany needed tanks desperately. The Eastern Front was consuming armoured vehicles at an unsustainable rate. Production could not stop for engineering refinements. Instead, the approach was to make incremental improvements while continuing production and accepting high loss rates from mechanical failure. The German response had been to make incremental improvements to later production models. The Ausführung A model, introduced in September 1943, had modifications to improve reliability. The Ausführung G model, introduced in spring 1944, had further changes, but these modifications addressed symptoms, not fundamental design problems. The Panther's engine was overstressed from the beginning. The Maybach HL230 had been designed for a tank weighing 30 to 35 tons. The production Panther weighed 45 tons. The engine was running 30% above its designed load continuously. This caused overheating. This caused excessive fuel consumption. This created conditions for the backfires and engine fires that plagued Panthers throughout the war. The transmission and final drive were similarly overstressed. The gearbox components were designed for lighter loads. When subjected to the Panther's actual combat weight, they wore rapidly and failed frequently. German field reports from Normandy in June 1944 noted that Panther engines typically lasted 1,400 to 1,500 kilometers before requiring major overhaul or replacement. But final drives failed much sooner, often after just a few hundred kilometers. German tank units in Normandy reported constantly cannibalizing disabled Panthers to keep others operational. The phrase used repeatedly in German reports was that Panthers had to be kept running through intensive maintenance, not that they ran reliably. The steering system used a clutch and brake mechanism that was inadequate for the Panther's weight. The clutches wore quickly. When heavy strain was applied during sharp turns or difficult terrain, the steering clutches would slip or burn out, exactly as British testers observed in 1948. The Panther Crew Manual, published July 1, 1944, included specific warnings about not overtaxing the steering system. The manual stated, "Also remember that it is not right and proper to torture the steering brake whenever one thinks it is necessary. This will break the engine quickly. Those who do this have no sense of tanks at all." This was not the language of a manual describing a reliable, well-engineered vehicle. This was the language of a manual describing a fragile vehicle that required careful handling to avoid catastrophic failure. The engine fires that destroyed the British test Panther in July 1944 and multiple Panthers during the 1948 trials were not anomalies. They were systemic problems documented throughout German service. German combat reports from throughout 1944 and 1945 repeatedly mentioned Panthers catching fire. A report from General Heinz Guderian dated June 28, 1944, shortly after the Normandy landings, stated that the Panther appeared to catch fire quickly. The German phrase was Der Panther brennt außerordentlich schnell. This was not new information to German commanders. The Germans had known since Kursk in July 1943 that Panthers had a severe fire risk, but the fundamental engine design problems that caused the fires were never adequately resolved during the war. The causes were precisely those identified by British engineers: backfires, igniting carburetor overflow, oil leaks from valve covers dripping onto hot exhaust manifolds, defective fuel pump seals, creating pools of gasoline in the engine compartment. A March to April 1944 German report described carburetor overflow wetting spark plugs, discharging unburnt fuel through exhaust header gaskets, causing fires on the outside of the motor. When British engineers examined the wreckage of their burned test Panther in July 1944, they documented exactly the same failure mechanism that German engineers had identified months earlier. The problem was known. It was not fixed. British tank crews who captured Panthers during the war and attempted to use them against German forces experienced these reliability problems firsthand. The most famous example was a Panther Ausführung D captured by the 4th Battalion Coldstream Guards, part of 6th Guards Tank Brigade, in Holland in autumn 1944. The German crew had abandoned the Panther during a retreat, claiming it had a transmission fault. British tankers found it apparently intact, started the parted engine successfully, and decided to press it into service against its former owners. They named it Cuckoo, painted large white Allied recognition stars on the hull and turret to prevent friendly fire incidents, and formed a crew from volunteers who learned to operate German controls. Cuckoo was photographed extensively, including an Imperial War Museum photograph showing it in action against Geisteren Castle on the banks of the Maas River on November 29, 1944. The British crews were impressed initially with specific aspects of the Panther. The 7.5 cm KWK-42 gun was powerful and accurate, far superior to the guns mounted in Churchills. The optical sights, Zeiss manufactured precision instruments, were superb, better than any British tank sights. The Panther's thick frontal armour provided confidence that German anti-tank guns could not penetrate it frontally. Cuckoo participated in several engagements over nearly 3 months of service with the Guards. The crews reported that when the Panther worked, it was formidable. The gun could destroy German tanks at ranges where German guns could not penetrate the Panther's frontal armour. The optics allowed precise engagement of targets at long distance, but Cuckoo required constant maintenance. The engine leaked oil continuously. The fuel consumption was enormous, far worse than British tanks operating in the same area. The steering needed frequent adjustment. The transmission, the component that had supposedly caused the German crew to abandon it initially, remained problematic throughout British service. It functioned, but it made concerning noises, grinding sounds during gear shifts, metallic clanking during hard manoeuvring. British mechanics worked on Cuckoo constantly between operations, trying to keep it running. After nearly 3 months of use, mechanical failure ended Cuckoo's service. Historical sources differ on whether the final failure was the fuel or pump system or transmission components, but all agree mechanical breakdown, not enemy action, ended Britain's longest use of a captured Panther in combat operations. No spare parts were available to repair whatever had failed. German Panther components were not interchangeable with British parts, and the supply chain for German equipment did not exist in Allied logistics. Cuckoo was withdrawn from service. The Coldstream Guards went back to using their Churchills and Cromwells, which were slower and less well armed than the Panther, but vastly more reliable. A Churchill might not penetrate a Panther frontally, but a Churchill would still be running at the end of a week of continuous operations. The Panther would likely be broken down waiting for parts and specialized maintenance. The French army had a similar experience after the war. France operated captured Panthers in the immediate post-war period, using them in French military units stationed in occupied Germany through the late 1940s. French maintenance reports documented constant mechanical problems, engine failures requiring replacement, transmission breakdowns, steering malfunctions, final drive failures. The French eventually abandoned captured Panthers because maintenance requirements were unsustainable. Despite having access to German spare parts stocks and German mechanics with Panther experience, the French could not keep these tanks operational reliably. By 1950, France had phased out captured German tanks entirely in favor of American-supplied Shermans and French-designed vehicles, despite the fact that on paper the Panther was superior to both in firepower and armor protection. What emerged from all these experiences, British testing in 1944 and again in 1947–48, German combat reports from Kursk through the end of the war, Allied attempts to operate captured Panthers in combat was a consistent pattern. The Panther tank was a maintenance-intensive, mechanically unreliable vehicle that required exceptional care and immediate access to spare parts to remain operational. In the controlled conditions of a factory test program, with skilled mechanics and full parts availability, a Panther could function adequately for limited periods. In actual combat conditions, with field maintenance, limited spare parts, and average crews under combat stress, Panthers broke down constantly. The statistics were undeniable. The British testing program, both the 1944 trials on the Soviet-provided Panther and the 1947–48 trials on REME-assembled Panthers, provided Allied intelligence with invaluable information. British and American tank crews facing Panthers in combat knew not to be intimidated by the tank's reputation. Yes, the Panther had thick frontal armor that was difficult to penetrate. Yes, it had a powerful gun that could destroy Allied tanks at long range, but it was mechanically fragile. Combat tactics evolved to exploit these mechanical weaknesses. Force Panthers into situations requiring mechanical stress, make them maneuver in difficult terrain, make them climb hills, make them reverse rapidly, make them fight in close terrain where they could not use their range advantage. The Panther's mechanical weaknesses became tactical vulnerabilities that informed Allied combat doctrine. British tank tactics in northwest Europe from summer 1944 onward specifically exploited Panther unreliability. Force the engagement into close terrain where Panthers could not use their superior gun range. Keep them moving and maneuvering until something broke mechanically. A disabled Panther was just as combat ineffective as a destroyed Panther, and Panthers disabled themselves regularly without needing to be shot. German reports noted that many Panthers abandoned on the battlefield had no combat damage, only mechanical failures that crews could not repair in field conditions. The story of British Panther evaluation is ultimately a story about the difference between engineering for specifications and engineering for reliability. The Germans created a tank that looked impressive in technical documents and propaganda films: thick armor, powerful gun, sophisticated suspension, advanced fire control optics. The British created tanks that worked. German Panthers had better armor protection on the front, better guns with higher muzzle velocity, better specifications on paper in nearly every category. British Churchills and Cromwells and American Shermans had mediocre armor by comparison, mediocre guns, unimpressive specifications in technical comparisons. But the British and American tanks kept running. They could be maintained in field conditions by average mechanics with basic tools. They did not catch fire spontaneously from design flaws. They completed their missions and returned to be serviced for the next operation. The 5 Panthers tested at Chertsey from February through mid-1948, all brand-new vehicles built under ideal conditions with quality German components and skilled assembly, could not complete a standard acceptance trial. Every single one failed mechanically before finishing the test program. One burned completely when the engine caught fire. One suffered catastrophic steering clutch failure. One had transmission gears strip under load. One had its gearbox destroyed when a broken torsion bar punched through the housing after brake failure on a slope. The fifth was cannibalized for parts before it could be tested because the others had failed so quickly. That fact, documented in official British Army reports, represents the final verdict on the Panther tank as a complete weapon system. It was not the wonder weapon of German propaganda. It was a mechanical disaster that consumed German resources, industrial capacity, skilled labor, and strategic materials while providing unreliable combat capability. The Panther required 2 to 3 times as many man-hours to build as a Panzer IV, used scarce alloy metals that Germany was running short of by 1944, and required highly skilled crews and mechanics to operate. Yet it broke down more frequently than simpler German tanks, and far more frequently than Allied tanks. From a strategic perspective, Germany would have been better served building more Panzer IVs, which were reliable, easy to maintain, and effective in combat, rather than pursuing the technically sophisticated but fundamentally flawed Panther design. The myth of German technical superiority in tank design died in the engine compartment fires and transmission failures documented by British test engineers at Chertsey in 1944 and again in 1948. The tests were methodical, scientific, and conclusive. The results were unambiguous. The Panther looked formidable. It had impressive specifications. German propaganda portrayed it as invincible, but when subjected to the same standard tests that British tanks passed routinely, it failed completely. Not once, but twice in separate test programs 3 years apart, using different vehicles from different sources. The conclusion was inescapable and supported by German combat reports from their own frontline units. The Panther was unreliable, prone to catastrophic mechanical failure, difficult to maintain, and unsuited for sustained combat operations. If you found this story compelling, take a moment to like this video. It helps us share more forgotten histories from World War II. Subscribe to stay connected with these untold stories, and we would love to hear from you. Leave a comment telling us where you are watching from. Our community spans from Singapore to Stockholm, from history enthusiasts to veterans. You are part of something special here. Thank you for watching, and thank you for keeping these stories alive.